Hello, dear classmates and Mr. Elias, and we are the group that presents the theme of nuclear fusion and fission. And first of all, let's start with the nuclear structure. So the number of protons in a nucleus is denoted by Z, and is called the atomic number. The total number of nucleons, which means protons plus neutrons, is called the mass number, and is denoted by A. The number of neutrons in a nucleus is denoted by N, with the formula N equals A minus Z. The electric charge of the nucleus is Z, where E is plus 1.6 multiplied by 10 in the power of minus 19. It is the charge of a proton. A nucleus with a specific number of protons and neutrons is also called a nuclide. And here you can see some diagrams that show the structure of nucleus with electrons, protons, and neutrons. And here is a visual representation of the mass number, atomic symbol, and atomic number placement. Next, here is nuclear fission, which is the process in which a heavy, unstable nucleus splits into two lighter nuclei. An example of fission is this equation, where the uranium-235 is hit by a neutron, and capturing it becomes excited and unstable. Thus, it quickly splits into two smaller dotted nuclei and two neutrons, as you can see by this animation. Note that the splitting was triggered by a single neutron that had just the right energy to excite the nucleus. Note also that during the split, two more neutrons were released. If each of these neutrons splits subsequent nuclei, we have what is called a chain reaction. And here shows the exponential growth. So this diagram also shows that there are first generation, second generation, third generation, fourth generation neutrons. And here is a schematic diagram of a nuclear fission chain reaction.
Okay, here are some requirements for fission and chain reaction to occur. So the enrichment is the process by which this percentage composition is increased to make nuclear fission more likely. Increased the proportion of uranium-235 above the natural value of 0.7%, typically to 3% by isotope separation processing. This is a critical mass, the minimum mass of uranium-235 needed for the reaction to occur. Otherwise, neutrons would not initiate the further reactions since they will escape. And naturally, neutrons that are produced by the fission reaction are very fast, so they have to be slowed down so that they can initiate further reactions. Typically, each fission or nucleus produces about 2.5 free neutrons, and for the first reactions to occur, we need one free neutron. So 40% of the neutrons are needed to sustain the chain reaction. Like here you can see the results of the release of the energy due to the fission reactions. As you can see, they're much more powerful than typical chemical chain reactions, reactions. The results of nuclear weapons and bombarding of Hiroshima city. The next is nuclear fusion. It is process of combining of two small nuclei into one large nucleus. An example of fusion is the reaction of deuterium with the tritium to form helium and neutron. In order to fuse two nuclei, you must overcome the repulsive force. So they will be close enough and strong enough to overcome this force. Yeah. Also, as a result of this reaction, we have a release of certain amount of energy as well. And one important thing to know is that the mass number and the like atomic number have to be conserved, so that the mass value and atomic value on the left hand side are equal to the mass value and atomic number on the right hand side. It is typical for any nuclear reaction. Okay, so deuterium is positively charged, so we need a certain amount of energy, kinetic energy, to overcome this electrostatic repulsion with the tritium, which is also positively charged, and it is more likely to be achieved with a high temperature. For example, this reaction is typical for stars that form helium by deuterium and tritium, because they have like a vast amount of energy due to their gravitational force. On Earth, we use fusion reactors that are using strong magnets, magnetic like force, in order to produce, like, to make it happen on Earth. However, right now the typical yield and energy inputs are more than outputs, so it's not like a very economically wise decision to do it right now. So it's only experimental nuclear fusion. The next topic is the binding energy. It's pretty important, and in the guide it comes out like as one of the understanding topics. So it is a minimum amount of energy required to completely separate nucleons, like protons and neutrons, of the nucleus. And in the same way, it is the magnitude of energy by which the nucleons are bound together. So if you want to like separate protons from neutrons in a nucleus, you have to have certain amount of energy, which is a binding energy. And the binding energy per nucleon, usually it means the stability of a nucleus. So the more the binding energy per nucleon, the more nucleus is likely to be stable. Its binding energy per nucleon, it's a pretty simple. So you just take binding energy. Usually it is written in mega electron volts unit, like its unit for energy, just like joules, but it's far more like far small than joules. So we use mega electron volts in nuclear reactions, and we divide this binding energy by the number of nucleons. So how much energy we need for to separate each nucleon. Here you can see the diagram that represents the relationship between nucleon number from 1 all the way up to 238, which is uranium, and against average binding energy per nucleon, megaelectron volts. As you can see, from the left side, it comes all the way to top and begin to decrease. So on the previous slide, I mentioned that the more the binding energy per nucleon, the more the nucleus is stable. So we can see like the upcoming trend to the nickel, 62, and after like it reaches this point, binding energy begins to decrease. So it the stability rises, then it falls. However, in some data, like it may be written that iron is the most stable of the nuclei, is the most stable nuclei. However, like actually this range between 62 and 56 is pretty stable. So either nickel or ferrum or iron, but it is preferred to use nickel. So don't be confused. Next, as I said before, like everything which is below by the means of nucleon number, then below than nickel, these elements are used and like are using other elements by like they're joining smaller nuclei are joining with other smaller nuclei to form bigger ones, so that they would reach iron or nickel, which are more stable, so that the nuclear fusion naturally occurs. On the other hand, this nuclear fusion, like the formation of smaller nuclei to ferrum and nickel, is typical for the stars. On the other hand, on the right hand side, we can see that number of nucleons is far greater than the number of nucleons for iron or nickel. So the bigger nuclei are splitting in order to be more stable and reach iron binding energy per nucleon, so that the nuclear fission occurs and they become more stable. Yeah, this is one of the tasks which requires to work with this diagram, which, by the way, can be found in the data booklet. Here we are asked to label with the letter S like the place where nuclei is the most stable, are the most stable. Oh, so let's take a look at the answer. Yeah, the Mars scheme says that S marked near line between 50 and 70. Look at the way that I did this. I just like put the crossed like lines from nucleon number, which is about like 56, I guess, like for iron, all the way up to the graph, and connected with the binding energy. And I mark this point as S as it requires. So this means I got like 1 point. Let's hop up to the next topic, which are the decay and nuclear transmutations, which is another type of nuclear reactions. The first type of decay is alpha decay. It is a decay of the alpha particle, which is a helium 42. So the, for example, the which is one plutonium, I guess. This nuclei is too large and to be stable, so it would decay alpha particle at a speed of around 5% of the speed of light into the more stable uranium-236 particle, so that the nuclear reaction will occur. During the alpha decay, the N and Z values are decreased by 2. Is the mass number or atomic number, like as you can see, and the A, like the mass number, is decreased by 4 for the two forming nuclei. This is because of the presence of the decay of the helium. So the alpha particle are very big compared to the particles that we'll talk about like next. So they can travel only several centimeters in air, and or a few tens or hundreds of millimeters through solids before they will be in rest and by the collision. The next is beta decay, which has 3 types. The first is beta minus. Usually, while speaking of just beta decay, we mean beta minus decay. For others, it will be clarified which one is it. If in the task it is written only beta decay, then it means beta minus. So for the beta decay, we have a transformation of neutron into a proton, and with the presence of the third particle antineutrino, which can be obeyed actually during the writing down the reactions. However, I just wanted to include that for you to know that this has its own energy, so that nothing is lost. If you want to calculate energy, it just transforms into another form. So this is the graph of the first of all, beta particles are much more faster than the alpha particles, precisely they're 0.995, the fraction of the speed of light. So it emits continuous spectrum of energy because of by looking at this graph, with the increase of energy, number of beta with its energy still present at any point, so the spectrum of energy is continuous. This is an example of beta decay, so that the decay of a cobalt 60 to nickel 60. We can see that cobalt 60 decays into an electron, like an element. which has the same mass number, but different atomic number, and the antineutrino. So typically the ratio between typically is the ratio between atomic number and atomic mass is too large for stability. So in beta minus, like the electron is emitted and the atomic number decreases by 1. And and A does not change. So here is an example of another type of beta decay. It's beta plus. On the contrary to the beta minus, it emits positron. As a result, which is a beta plus particle, and if in beta minus the z value decreases, increases, here it decreases by 1. And that ratio is still not stable. It's too small, so the positron is emitted. And here we have not antineutrino but neutrino. Here is an electron capture. It's an example, a different example of beta decay. So the typical formula is proton plus beta minus particle, which is electron, neutron plus neutrino. Here is an example of electron capture where beryllium-7 is taken. Then the electron is added in order to get to the electron is not added, taken in order to get to lithium-7, which has Z value decreased by 1 in comparison to beryllium. However, the mass is still the same. So and one more time, neutrino is emitted. Here is an example of gamma decay. In the contrary to the beta decay, the energy spectrum is not continuous. It has definite kinetic energy that it can emit, so that the radiation of gamma decay has constant energy values. What else? Like an excited nucleus, for example, SR90, the star, it means it is excited. It's bombarded with high energy particles. It can decay to the ground state by emission of gamma ray photons. It's one form of energy with typical 10 kilo electron volt to 5 mega electron volt range of energy. So this process is called gamma decay. As you can see, on the left we have the same nuclei that on the right. However, it is in an excited state, and this one is not. Sorry. So that the A and Z values are not changed. So the next topic, subtopic is half-lives and decay constant. Radioactive. The first thing you have to know is that radioactive decay is random and spontaneous. So it cannot be controlled or predicted. The decrease is a statistical process. There is no way to predict when any individual nucleus will decay. The rate of decay is not affected in any way. Like no physical, no chemical change, heating, cooling, none of this can affect radioactive decay. For different nuclides, this rate varies with a wide range. The decay constant, which is like lambda, is the probability of decay per unit time. Here is the formula for the amount of remaining nuclei with the given initial amount of nuclei times E, which is a constant, raised to the power of negative lambda, which means that this is a decreasing trend times time, multiplied by time. So that it depends to the time. We can see that at the period of time 0, we have 250 undecayed nuclei, which is if we're going to substitute values to this formula, means that n equals n0 at t0, which is pretty logical, so that the initial number of nuclei is 250. However, as the time passes, this number will decrease, and it will decrease exponentially. And this is called exponential decay law. Okay. Here's an example of decay of thallium 208 to lead 208. As you can see, it is followed by the beta minus decay. So looking at the graph, we can find the initial number of nuclei. You can do it by yourself. And we can see that every 3 minutes, value for value for the remaining nuclides of thallium 208 decreases by 2, which means that 3 minutes is the half-life of the thallium 208 decay. And number of thallium nuclei decrease exponentially as well. What is a half-life? The half-life is the time required for the number of radioactive nuclei to decrease to 1/2 the original number. Going back to the thallium, we can see that we have initially how much 1.6 times 10 to the raised to 22 nuclides at t0. However, at t equals to 3 minutes, we have exactly 0.8 times 10 to the raised and 22 nuclides, which is exactly the half. So that 3 minutes is the time it takes for the number of radioactive nuclei to decrease to 1/2 of the original number. The formula that it can be expressed with is a half-life formula, which is half-life equals to natural logarithm of 2 over lambda, or 0.693 over lambda. You can get this value by the calculator. Actually, this formula and this one, they are in your data booklets, so you don't have to memorize them, just know how to use them. In addition, there are additional formulas for the remaining nuclei, initial nucleides ratio, for example, if we are given the fraction, we can easily find like other values, such as time or decay constant. And also this one equals to 1/2 to the power of n. And from this, we can obtain that like what is n actually? N is a number of half-lives. Number of half-life equals to the total time of the decay divided by the half-life value. So the example of this is like a sample of carbon-11 has an initial mass of 4.0 times 10 to the raised to times 10 raised to minus 15 kilograms. It has a half-life of approximately 20 minutes. Calculate the mass of carbon 11 remaining after 1 hour has elapsed. The first thing to know is that according to the formula, yes, we're using the number of remaining nuclides. However, if we are going to change this value to the mass, then it would not affect, and we will obtain another formula, like remaining mass equals to the original mass times E raised to minus lambda T. So by this, we can have one of the solutions. Actually, there are 3 of them. Let's look at them. Yeah. So the first solution involves the formula of the half-life that I showed to you, like this one. We just have to rearrange the values so that we're given half-life. We know what's natural logarithm of 2, so we can easily calculate the decay constant, which is this value. We know that m is proportional to the number of remaining nuclides, as I said before. So by plugging in the values to this formula, we know the initial mass, we know that we calculated the decay constant, and we know the time after after 1 hour has elapsed. Sorry. So for this, like plugging in the values, we have this mass after 1 hour. Here is an example and another solution, which involves another formula. So we're simply calculating the number of half-lives. Then we're plugging in to the different formula. We're plugging in this value to the different formula to obtain that mass equals to the same value. Or we can do it graphically, like we know the initial value. We know that 60 is like 3 half-lives, and like incrementally decreasing the remaining mass by 2 with each half-life, we get to the same value. So there are many different solutions for this. Let's go to the different topic, which is the emission spectrum of the stars. Like, as you know, each element, not emission, absorption, I'm sorry. As you know, each element has its own absorption spectrum that we studied in topic 2, as I recall correctly. For example, for hydrogen, this black lines means that this particular wavelengths or frequencies are observed. So that for helium we have different absorption spectrum, and we can differentiate between the elements in this easy way. And by comparing absorption spectra of stars with the absorption spectra of known elements, we can get to the elemental composition of the star. For example, the sun's spectrum, the sun's hot interior spectrum is continuous at any point. This means none of the spectrum is absorbed, so no gases. However, as we get cooler to the atmosphere, such gases as hydrogen, helium, and others are begin to absorb spectrum of the sun. So we get to this composition, and we can get to certain conclusions. Oh, sorry. Looking at this, I think it reminds you the different energy change levels are responsible for different absorption spectra. For example, if we're talking about this like particular red color absorption, we're talking about the energy level change from N2 to N3. For this, from N2 to N4, and by looking at these energy levels, we can get to the understanding of the composition of the star gases. Yeah. So that's it for this topic.
Hello, my name is Mohammed, and today's first exercise is which of the following is an alpha particle. So let's go through each one. Answer choice A represent a gamma particle. This is a high energy photon, and it has virtually no mass, no charge. So it's not A answer. Now B represents an electron, also known as a beta particle. It has a mass of virtually zero. Relative to protons and neutrons, it's very light, and charge is -1. Next, we have an antiparticle of an electron, known as a positron. So the positron has the same mass of an electron, but with an opposite charge. The charge is positive, one as opposed to -1. Next, we have alpha particle, which is the nucleus of a helium atom. It has 2 protons, 2 neutrons. So as you can see, it has mass of 4 and charge of 2, which is also the atomic number for elements as well. So D is the answer. And then E represents a neutron. A neutron has a mass of 1 and charge of 0 because it's neutral. And the alpha particle, you can also write it this way, with an alpha symbol instead of helium symbol. So the next exercise is which of the following processes converts a neutron into a proton. So let's go through each of one. So first is alpha decay, and we will take uranium-238 and undergoes alpha decay to increase its stability. Now if it undergoes alpha decay, or what is the missing particle, or what is the element that is produced? 238 minus 4 is 234, and 91 minus 2 is 90, which means now let's analyze the number of protons and neutrons. This is by the way thorium-234, and thorium always has an atomic number of 90. Thorium-224 and thorium-230, they are isotopes of each other. They have the same number of protons but different numbers of neutrons. Now uranium-238 has 92 protons. Thorium-234 has 80 protons, 90 protons. The atomic number gives the number of protons. Now the number of neutrons is the difference between a mass number and atomic number. So 238 minus 92 is 146, and 234 minus 90 is 144. So notice that the number of neutrons decreased by 2, and the number of protons decreased by 2. So alpha decay will always decrease the number of neutrons and protons by 2. It decreases the mass by 4. It doesn't convert a neutron into a proton. It simply reduces the number of neutrons and protons in an element, so it's not going to be alpha decay. Now let's take a look at positron decay. Let's start with the sodium-22. It undergoes a positron decay, and it produces neon-22. So we can see the mass and the charges are balanced. Now sodium has 11 protons and 11 neutrons. Neon has 10 protons, 12 neutrons. So notice that the number of neutrons increased by 1 and the number of protons decreased by 1. That means that a proton was converted into a neutron because the number of protons went down by 1 and the number of neutrons went up by 1. And so positron production, it decreases the number of protons but increases the number of neutrons. But we're looking at something that converts neutron into a proton and not a proton into a neutron. So B is eliminated from that choice. The next one is gamma decay. So let's say if we have an energetic element, let me use an example. Let's use the same sodium-22. Let's say that it has a lot of energy and it emits some of that energy in form of gamma radiation. Notice that gamma decay does not change the mass or the atomic number. So therefore, it's not going to convert a neutron into a proton. Gamma decay simply reduces the energy of nucleus. Now let's talk about beta decay. I'm going to use iodine 131. When it undergoes a beta decay, as mentioned before, is going to give us xenon. So iodine has 53 protons, xenon has 54 protons, and then 131 minus 53, that's 78 neutrons, and 131 minus 54, it's 77 neutrons. So the number of protons increased by 1, and the number of neutrons decreased by 1. So we could say that a neutron was converted to a proton since the number of neutrons decreased by 1 and the proton increased by 1. So D is the answer we're looking for. So beta decay will convert a neutron into a proton. Now let's take a look at electron capture, which is the last possible answer. And I'm going to use mercury 201 for for this example. Now electron capture, the electron has to be on left side as opposed to the right side. So what it happens is the nucleus captures one of the inner core electrons, and a nuclear reaction occurs. 80 plus negative 1 is 79, and so gold has an atomic number of 79. Mercury has 80 protons, gold has 79 protons. Mercury has 121 neutrons, gold has 122 neutrons. And so we can see that the number of protons decreased by 1 and number of neutrons increased by 1. So in this example, proton was converted into a neutron, and so we could eliminate an electron capture. So D as the answer of beta decay converts a neutron into a proton. Last task is identify the unknown element. In this example is we take uranium-238, is struck by a neutron, and as a result it produces 3 alpha particles, 2 beta particles, and some missing element. What is the known element? Well, we need to balance the equation firstly. So let's balance the mass number first, and then we can balance the atomic numbers and the charges. So on the left side, focusing on the numbers on the top, the mass numbers is 238 plus 1 on the left side, and that has to equal the mass on the right side. So we have 3 alpha particles with a mass of 4. That's going to be 3 times 4, and the mass of the beta particle is 0. And let's say X is the mass of a known element. So 238 plus 1 is 239, and 3 times 4 is 12. So X has to be 238 minus 12, which is 227. So that's going to be the mass of the unknown element. Now let's calculate the atomic number. The unknown element So focusing on the bottom numbers, on the left is 92 plus 0, and then that's equal to the 3 times 2 plus 2 times -1 plus some unknown letter or unknown value y. 3 times 2 is 6, 2 times -1 is -2, and 6 minus 2 is 4, 22 minus 4 is 88, so that's going to be atomic number of the element, and that corresponds to a array radium, so that is the unknown element in this example, radium-227.
The next subtopic is radioactive waste. It divides into low-level nuclear waste and high-level nuclear waste. So firstly, low-level nuclear waste are gloves, paper towels, protective clothing used in areas where radioactive materials have been handled, like hospitals with cancer treatment. Low-level nuclear waste has a short half-life and low radioactivity, but is produced at high volumes. Also, low-level nuclear waste can be stored in cooling ponds until the radioactivity has fallen to safe levels. So moving to high-level nuclear waste, it is spent reactor fuel and waste from the reprocessing of spent fuel. High-level nuclear waste has high levels of radioactivity, and the isotopes have long half-lives. Also, high-level nuclear waste can be converted into a solid glass. Which this process is called vitrification, and it can be stored in stainless steel containers, which are stored deep within the earth in geologically stable locations. So next, we'd like to talk about fast breeder reactors. It is a nuclear reactor that generates more fissile materials than it consumes. So I'd like to clarify that fissile material is a material capable of sustaining a nuclear chain reaction. And so fast breeder reactors were developed because the supply of fissile uranium-235 is limited, while non-fissile U-238 is more abundant. So here are the formulas that show the reaction. So in this reaction, non-fissile uranium-238 is converted to fissile plutonium-239, as plutonium-239 is able to sustain a nuclear chain reaction. So the first reaction is neutron capture, where the nuclei absorbs a neutron to form a heavier nuclei. And the second reaction is beta-minus decay. And the third reaction is also beta-minus decay. And finally, the last reaction is nuclear fission, where plutonium is bombarded by neutrons.